In this video, we're going to look at the probability of the intersection of dependent events. Determine the following probabilities using the product rule for the intersection of dependent events and write your results as a simplified fraction. So we saw that the probability for independent events, E1 and E2, so and is the intersection, was you just found the individual probabilities and multiplied them times each other. It's just a little bit different for dependent events. You find the probability of the first event, and then you find the probability of the second event given that the first event happened. Now, so this is a conditional probability, and this sounds a little bit fancy, but we're going to find in practice it's not too hard to find this probability. We're just going to change our sample space a little bit like we did with conditional probabilities. So let's look at the first one. 2 names are drawn from a hat of 15 names without replacement. So since it's without replacement, that's how we know it's dependent event, because the second one will have a different probability because some first name is drawn and that will affect the second one. To determine who will be responsible for driving to a sporting event. If there are 8 women and 7 men, we want the probability that the first person chosen is a man, and, so that tells us its intersection, the second person chosen is a woman. Okay, so we're going to find these 2 probabilities separately. So the first person is a man. Well, there's 15 people in total and 7 men, so this is going to be 7 out of 15. Now we want the probability the second person is a woman, given that the first is a man. Okay, so again, this looks a little bit fancy, but all you have to think is, well, we had 15 names in the hat. 1 person was drawn. Okay, so now there's 14 names left. So that's our reduced sample space. And we know that first person was a man, so that means there's still 8 women names in the hat. So its second probability is 8 out of 14. And now you just find their product. So 7 out of 15 times 8 out of 14. Okay, again, I'm going to do a little simplifying first. 7 and 14 have a common factor of 7. 8 and 2 have a common factor of 1. And now we can multiply across. 1 times 4 is 4 out of 15. Let's look at the next one. 2 cards are drawn from a deck of 52 cards without replacing the first card before choosing the second. So without replacement, again, that's a key indicator for dependent events. Find the probability that the first card is a club, and, so n tells us at its intersection, the second card is a red jack. Okay. So the probability of the first card is a club. Well, again, looking at our cards, here are the clubs, okay, which is 13 out of 52, or 1 out of these 4 rows. So you can write that as 1/4. Now for the second card, we're going to be a little bit, not more careful, but we're going to have to be careful. The probability of the second card being a red jack, and again, we have given that the first was a club. So that changes things a bit. We can't just count the number of red jacks out of the total number of cards, because since 1 club was definitely chosen, we don't know which one, there's only 51 cards left. Okay, and let's see how many red jacks are there. There's just 2. So the second probability is 2 out of 51. And now we will find their products. So 1 out of 4 times 2 out of 51. I see a common factor of 2. And now we can just multiply straight across. And 51 times 2 is 102. So 1 out of 102. Last question. 2 letters are chosen from A to Z for a password. The letters must be different from one another. Okay, so this is another way of saying without replacement, or specifically without repetition and without replacement are the same idea. So the letters must be different from one another. Whatever the first letter is, the second letter can't be that letter. So we can think of reducing the sample space on the second choice. So it says find the probability that the first letter is a vowel and the second letter is a Z. Okay, so let's not write all of these out. We're just going to put them underneath here. So the probability that the first letter is a vowel, well, we said 5 out of 26 cards are vowels. And for the second letter, only one of them is a Z, but we've already chosen a vowel, so there's only 25 cards left. So we have 1 out of 25 is the probability the second letter is a Z. Now we can find this product. Let's do this in red over here to the left. 5 over 26 times 1 out of 25. I see a common factor of 5 I'm going to cancel. So that reduces to 1. This reduces to 5. And 1 times 1 is 1. And 26 times 5 is 130. So 1 out of 130.